Okay, thanks, Lexing. Just a quick check. Can everyone hear me all right? Yeah, all good. And you can see the slides. All right. Okay, thanks everyone. So seems like we have a lot of people here. It's actually much more than what I got in your conference talk. So thanks for coming to my PhD conclusion talk. So I'm very excited to give you a presentation on what I have worked on over the past 4 years here. So my thesis is entitled Measuring Collective Attention in Online Content, which I studied from 3 aspects: sampling, engagements, and network effects. So I started with one typical pathway of how users consume content on the internet. The users browse the social networking sites like Twitter and Facebook. Some external link show up in their social feeds, and the user can follow this link to other websites. In this example, a YouTube video is shared on Twitter. So user can consume products on the media sites, like watching a video, listening to a song, or reading a book. So if we take a user-centric viewpoint, the users actually have some decisions to make. First, they need to choose which product to click. And second, once they click, they need to decide how they engage with those products. And those 2 decisions can be well captured by a 2-step framework, which was also used in the MIT Music Lab experiment. However, we are not the platform owners, and we don't have user log data in most time. So therefore, instead of taking the user-centric viewpoint, we choose to take an item-centric approach. The 2-step framework actually corresponds to my research questions. First, I want to understand the effects of platform recommendations. How does the recommender system drive user attention? And second, I want to study the pattern of collective user behavior. Why are some products more engaging? Furthermore, since I manually use social media preference as a proxy to decide which item to include in my dataset, it's crucial to first understand how social data sampling could potentially affect my observations. So here is the outline of this talk. I have discussed the scope of my research. Next, we will go through the 3 research questions in details. Let's start with the social data sampling study. So one full paper accepted in ICWSM 2020 is produced from this work, along with a new dataset and a new software for reconstructing the complete filtered stream on Twitter. So in social media studies, Twitter is the prevailing data source. On the left figure, I show that 31% of ICWSM papers in the past 6 years have used the Twitter data. However, Twitter public APIs subsample the data if user requests too much data. Twitter offers 3 free APIs: search, sampled streaming, and filtered streaming. Because of the rate limiting, most studies that use the search API or sampled stream are subject to data sampling. This table describes API usage, rate limited condition, and affected studies in detail. So our work concentrates on the filtered streaming API. In a widely used USC COVID-19 dataset, we estimate it only covered about 5% of all matched tweets. So data sampling is pretty substantial for some work. So we ask 2 questions in this section. First, how are the tweets missing in the filtered stream? And second, what are the effects on common measurements? So our contribution is a comprehensive measurement study of the Twitter sampling effects across different timescales and different subjects. So the filtered streaming API collects tweets matching a set of prescribed predicates in real time. For example, tracking all tweets with keyword COVID-19. So in each second, no more than 50 tweets will be returned. So what will happen if over 50 tweets are matched? It turned out that a rate limit message, which indicates the cumulative number of missing tweets, will be returned. So the red lines here are the rate limit messages containing an integer and a timestamp. So if we compute the difference between two rate limit messages, we should be able to estimate the number of missing tweets within a time interval. Like the first two messages here suggest that 208 tweets are missing in this one particular second. So to reconstruct the complete filtered stream, we split the filtering predicates into multiple subcrawlers. We curated two data sets. One is related to cyberbullying and the other is about YouTube video sharing. We split the 25 cyberbullying keywords into 8 subcrawlers. From the last column of this table, we can see that each subcrawler now has over 99% sampling rate. In contrast, if we use one crawler with all keywords, we can only get 52% of all desired tweets. We want to validate the accuracy of Twitter rate limit messages. We obtained a data copy from the Firehose service, which provides the complete Twitter data. Our estimate volume from the rate limit message is plotted as the red line, and the Firehose is plotted as the gray line. So visually, those two lines overlap with each other. The error measured by MAPE is also very small. So the result indicates if one has a downsampled data set and the rate limit messages, they can actually estimate how, the volume of complete sets and therefore the sampling rate. In the bottom figure, the blue circles are the correct tweets from a single crawler. The green number is our estimate missing volume. Our estimate missing volume use rate limit messages. We can see that it can only estimate the numbers, but not the contents of missing tweets. Now we add up the obtained tweets from multiple subcrawlers. The black crosses are the tweets in the multiple subcrawlers, but they are not in the single crawler version. So the difference is also negligible. So those those three numbers listed in the bottom are almost the same, but multiple subcrawler can obtain the tweet contents of Firehose stream. Next, we look at temporal variation as shown in those two figures. The x-axis is the timeline, while the y-axis is the temporal sampling rate. On the left figure, the hourly sampling rate is influenced by the tweeting activities in different time zones, while on the right figure, the millisecond sampling is heavily affected by the platform design. The sampling rate peaks at millisecond 657 and drops monotonically after that. So having introduced the rate limit messages and the temporal variation, we then measure the sampling effects on common measurements. We examine whether or not we can use a Bernoulli process with the average sampling rates to approximate the empirical observations. This assumption is widely used in pilot studies, but has not been validated. We use this statistic as an error metric, which computes a numerical distance between two distributions. First, if we know the true frequency in the complete stream, can we estimate the sampled frequency? The left equations give the binomial distribution and expected frequency. In the middle figure, x-axis shows different value for the complete frequency. Y-axis is the error metric. We can see the errors are all very small. In the right figures, the x-axis is sampled frequency and the y-axis is the probability. So if a user posts 20 tweets, the plot shows that the probability distribution for the number of tweets we will observe in the sampled stream. So the binomial distribution align well with empirical data. The dashed vertical lines here denotes the mean value. On the other hand, if we only observed the sampled stream, can we infer the true frequency in the complete stream? We can do it by using negative binomial distribution. The bottom left equations are the PDF and expectation of negative binomial distribution. The bottom middle figures present the error metric with different sampled frequency. The error are also very small. So the bottom right figure shows that if we observe a user posting 13 tweets in the sampled stream, and the sampling rate is around 0.5, then it's most likely that this user actually posted 22 tweets in the complete stream. So in this slice, we investigate that if we only have the sampled observation, can we estimate the true ranking of the complete set? In the left figures, the x-axis shows the most active 100 users in the sampled set, while the y-axis shows the most active 100 users in the complete set. So the ranking is based on the number of tweets they post. If the ranking in the sampled sets can capture the true ranking, then all circles should fall along the diagonal line. But in fact, we observe a moderate disagreement in the ranks. So the color of each circle indicates the user sampling rate. Blue is high sampling rate and red is low sampling rate. In the middle figure, we zoom into the blue users and the red users and investigate what makes their sampling rate different. We found that the blue users disproportionately post during the very high sampling rate period at millisecond level. On the contrary, the red users often post during the low sampling rate hours. Recall that we can use negative binomial distribution to estimate the true frequency. We can correct the observed ranking. So in the right figures, we can visually see the circles all move towards the diagonal line. Kendall tau also shows the agreement between those two ranked lists is improved. We also identify stronger risk in diffusion models. Two prominent features used in modeling tweet cascades are the inter-arrival time and user inference. Here, I show an example cascade. The full circles are the observed tweets. The empty circles are the missing tweets. The x-axis is the elapsed time since the root tweets, and the y-axis is the number of followers for the retweeting user. Not only the sampled cascade missed about 30% of the retweets, most importantly, it missed the most influential user. This will substantially compromise the model accuracy. For the whole dataset, the distribution of the inter-arrival time is changed. The median value is 23 seconds in the complete set. However, it increased almost fivefold to 106 seconds in the complete set. So to sum up this section, we present a comprehensive study of the tweet data sampling effect. We start with the question that how are the tweets missing in the filtered stream? We find that the volume of missing tweets can be estimated by rate limit messages, and the tweet sampling rate varies across different time scale. Next, we have a fruitful of observations on the measurement fidelity. First, the Bernoulli process with a uniform rate can approximate the empirical entity distribution well. Second, the true entity ranking can be inferred based on sampled observation. Third, sampling compromises the quality of diffusion models, since the inter-arrival time is significantly longer in the sampled stream, while user inference is lower. So in the next two sections, we will use YouTube as a lens to study collective user behavior on the media sites. We first try to understand the network effects induced by the recommender system. So a full paper and a short paper are produced from this work. The full paper is accepted in CW 2019, which also won a Best Paper Honorable Mention Award. The short paper is currently under review. This is a joint work with Minzhang Xin, Alastair Tran, and other folks in our lab. So we also released a new dataset, a new demo. The recommender system are ubiquitously on modern online platforms. Much effort has been on generating more accurate recommendations. As we can see, the paper list on YouTube recommender system. However, relatively little is said about the effect of recommender system on overall user attention. In the right figures, I show a video web page. We can see a list of recommended video on the right-hand panel. The videos naturally form a directed network, and the directions imply how user can navigate between video by following the platform recommendation. One can conceptualize those links act as control for user attention to flow. So we ask two questions in this section. First, what does the recommendation network look like? And second, what are the network effects on video popularity? Our contribution is the first large-scale study on network effects induced by the YouTube recommender system, and a new model for estimating the attention flows over the network. Let me show you an example on how YouTube recommender system drives user attention. This plot shows a network of 6 videos from artist Adele. The node size is proportionally to videos' cumulative view count. The edge indicates the recommendation given by the platform. Some videos are not directly connected, but they are reachable within a few hops. When the video Hello was released, it attracted a huge amount of attention. On the right figure, we found multiple old videos from Adele receive a traffic spike on the same day, even for 3 videos that were not directly pointed by Hello. This example shows that the viewing dynamics of video connected by the recommendation links may correlate with each other. And it promotes us to investigate the pattern of attention flows among them. So having shown you a network of 6 videos, now we want to, how does it look like for thousands of videos? We curated a new dataset called the Web Music Graph dataset, which contains 60,000 videos from the complete set of Web artists. We focus on music video because they are the most popular category on YouTube. We chose not to track individual users. Instead, we use the relevant list from YouTube Data API because it's not personalized, it's consistent across API calls, and it changes less frequently. We tracked our recommendation links for 6 straight days. The number of links ranged from 337,000 to just under 400,000 every day. So below is a visualization of starting from video Hello, which video can be reached within 3 hops. The color of the nodes correspond to the view count of that video, and the size correspond to the in-degree value. This plot contains some of the most popular videos on YouTube. They sit in the center and they link to each other. We discovered the popularity bias in the recommendation network. We divided the video into 4 equal-sized groups by computing the view count quartile, shown as the 4 bubbles here. Each group contains about 15,000 videos. The top 25% group on the left contains the 25% most viewed video, while the bottom 25% group on the right contains the 25% least viewed video. We then count the number of edges that originate and end in every 2 groups. So the width of the arrow is scaled by the number of edges. We observe that every group disproportionately points to more popular groups than towards the less popular groups. This means the recommendation network built by the platform is likely to take a random viewer to more popular videos and keep them there, therefore reinforcing the rich get richer phenomenon. So we also measure the network by using the bow-tie structure, which was first proposed in early 2000s. The left plot here is how the web structure looked like in 1997. The bow-tie structure divides the graph into 5 components. So the central part is the largest strongly connected component, LCC. The in component contains nodes pointing to LCC, but not reachable from LCC. The out component on the right contains nodes that can be reached by LCC, but not pointing back to LCC. So using the same approach, We show the biotype structure of our Weber network on the right. We can see the style of two biotypes are quite different. The Weber network has two imbalanced tile with a much larger in component. So now I replace the left plot with the attention biotype, in which we resize each component by the daily view count for all the videos inside. Because of the definition of biotype structure, attention between components can only flow along one direction. That is from the in component to the LCC, then to the out component. The central LCC consists of less than 25% of videos, but it occupies more than 80% of the attention. In comparison with the structure biotype, the in component shrinks from 68% to just 12%. So the in component contains lots of videos, but they don't attract much attention. So having defined and measured the network, we move to the question, can we better model video popularity with the network information? On the left plot, so each sequence is the view count series for a video. We notice there is weekly seasonality, so we use a seasonal naive model as baseline, which copies the observation from the last cycle. So there is also strong autocorrelation. So we use autoregression model as a baseline, which learns the relation from the past 7 days. We also implement an LSTM model, which is a sequence-to-sequence model, and it predicts the next 7 days at one go. We end up with a combinational model that uses an autoregressive part to model the user latent interest and a linear part for the network contribution of each persistent link. The bottom figure illustrates our design. Here are two view count series for two videos. They are connected to each other. The predicted views are affected by its own past history, as well as the view contributed by its incoming neighbors. We show that the proposed ARNet model outperforms other baselines. We use SMAP as error metric. The lower is the better. So by using the ARNet model, we can also compute the network contribution ratio. This is defined as the amount of views contributed from the network against the estimated total views. We asked the question that if the recommender system were to be turned off, which artist will be affected the most? On the x-axis, we compute the popularity percentile at the level of artists, but with the estimated network contribution removed. On the y-axis, we compute the difference between the true popularity percentile and the network removed popularity percentile. So the outliers here denotes artists who gain much more popularity through the network than their peers. The left figure gives evidence that the recommendation network can help some artists massively increase their popularity. We take a closer look at the outliers by scatting them on the right figures. We noticed a group of indie artists and hip hop artists are more heavily relying on the recommendation network to become popular. We also developed a new demo called Attention Flow, which is designed to visualize a collection of time series and the dynamic network influence they have among each other. User can interactively choose the time slider, and the system will visualize the inference network within that period. The ego node is located on the rightmost side of the time slider. In this example, video rolling in the deep. And once user hover on another node, here is video Someone Like You, this system will show the inference between those two videos. The red colored edge quantifies the views that the hovered nodes received from the ego node. And the blue colored edge shows the views that the hover nodes contribute towards the ego node. So to sum up this section, we present the first large-scale study on the video network induced by the YouTube recommender system. We used the YouTube data API to build a non-personalized video network. We measured the network from different perspectives. In particular, we discovered the popularity bias and unequal attention allocation in the recommendation network. Finally, we propose a model that takes account of the network information. We estimate the link strength for each recommendation links, and we generate new insights based on the modeling results. So after discussing my work on the network popularity, I move forward to the engagement study. Once the user click on a product, when will they stop watching? So I will describe the aggregate engagement patterns on YouTube and how to predict it. A full paper and a demo paper are produced from this work. The full paper is accepted in ICWSM 2018, and the demo paper is accepted in the Web Conference 2018. We also released a new data set and a new software for collecting YouTube video data. Let's start with a motivation example. So the left video is about President Obama awarding a medal to Joe Biden, and the right video is an Indian Bollywood video. If we look at the number of view count they have accumulated, the Bollywood video is much more popular, have 2 times of the views of the Obama video. However, if we look at another metric to compare how much time they have drawn from the audience, the Obama video has 62 years watch time, while the Bollywood video has only 32 years. Note that both videos are of similar length. This example shows that video view count does not translate to video watch time. In fact, watch time is the central metric in YouTube recommender system. Hence, we argue that for both content producer and the content hosting platform, watch time is more important than the view count. Also, this example shows that we don't observe watch time for each viewing session, nor for each users. Instead, our observation is aggregates on the video level. So I use the term popularity and engagement to differentiate user behavior in online platforms. Popularity metric describes the behavior of choosing a product, and it's known to be affected by clickbaits and social promotion. On the other hand, engagement metric describes the post-clicking behavior, such as watching, commenting, and sharing. Here, I detail example of popularity and engagement metric in different domains. We can see that both metrics have been studied. However, for videos, most of the current work still focuses on popularity metric. There are some early work on video watching behaviors. However, our work differs results from 2 perspectives. First, we don't use any browser extension which is known to be labor intensive and not scalable. Second, we set up our prediction task in a cold start fashion. This is without using any user reaction such as views and likes. So in this section, we ask 2 questions. First, how to measure aggregate engagement. Second, can aggregate engagement be predicted? Our contribution is the first large-scale measurement study of how users collectively engage with online content, and a new metric to describe content quality. We have constructed a new data set called Tweeted Video Dataset, which contains 5 million videos published and tweeted across 2 months span in 2016. A video screenshot is presented here. On the left side, we show that the available features, we can crawl information about video metadata such as length, channel identity, and text description. Moreover, and shown on the right green box, this dataset contains 3 time series about user attention attracted by this video: daily view count, daily watch time, and daily share count. we can easily derive other metrics such as average watch time. We remark that our tweeted video dataset is the only public available dataset that contains information about user watching behaviors. We start with the average watch time, which is plotted on the y-axis. On the x-axis, we plot the video duration. We group video with similar lengths into a bin box. Here, we split the x-axis to 1,000 equally wide bin. Each bin has 50 to 40,000 videos. Within each bin, we show different percentile by different color shades. The darkest line in the middle maps to the median value. We can also divide the watch time by video length and use the same approach to get the plots of average watch percentage. We call those two plots engagement maps. We observe that both engagement maps have an underlying trend. Average watch time is positively correlated with video length, while average watch percentage is negatively correlated. They are both intuitively correct. People tend to spend more time on longer videos, but they are more likely to watch a shorter video toward the end. So this brings a question. If two videos have different durations and different watch measures, which one is better? Here, I show two examples. The left video is a short video about kids doing karate, and the right video is a much longer video of a live fighting show. So if we compare those two videos, watch time and watch percentage will give us opposite results. The karate video has a much higher watch percentage, while the live fighting show has a longer watch time. To solve this question, we propose a new metric called relative engagement based on the engagement map. The blue plot maps watch percentage to rank percentile among video with similar length. The legends along this vertical dashed axis are the value of relative engagement, which lies between 0 and 1. The new relative engagement metric allows us to compare video across different lengths. So from the view of relative engagement, we can see that the karate video and live fighting show video are equally good, and this information cannot be obtained directly if we are just using watch time or watch percentage. Having defined a new metric, relative engagement, we now study its characteristic. To assess the relationship with video quality, we construct two sets of quality data sets in the category of music and news. Random music and news datasets come from the subsets of tweeted video datasets. Viral music video and top news video are both produced by professional companies. Billboard top hits are the most popular 100 songs each year. We consider there is a quality improvement from random music video to viral music video than to the Billboard video. And there is also a quality improvement from random news to top news. We plot the tweeted music video and the tweeted news video in the same fashion of relative engagement map. We then place the plots of quality video on top of it. Nearly all Billboard video have a high value of relative engagement, sitting over 0.8. And so generally, we find that the value of better quality videos are shifted towards the end of higher relative engagement. The same trend also presents in the news video, in which we plot on the right figure. So those two examples show that relative engagement is one plausible surrogate for video quality. This finding is consistent with previous work that post-clicking behavior is only relevant to product quality. Next, we study the temporal dynamics of relative engagement. On the left plot, x-axis is video age. The y-axis on the left is the daily view series corresponding to the black line. It's known that the video view series appear to be very bursty or have a complex rise and fall pattern. The y-axis on the right is the relative engagement score corresponding to the green line. We find the relative engagement is rather stable over time. This motivates us to measure the temporal change of relative engagement for the whole dataset. On the right plot, the red lines shows that nearly 93% of videos, they don't change over 0.1 in relative engagement from day 7 to day 30. The stable temporal trend in engagement is very important, as it suggests that one can forecast the future engagement easily if early signal is observed. So this also motivates us to set up a prediction task to predict engagement metric. And in particular, I want to predict engagement in a cold start setup. That means we don't use any user reactions such as early view number, likes, or comments. We show our prediction features on the left blue box, such as duration, topic, and channel. All the features can be obtained before a video gets uploaded to the platform. The targets are to predict relative engagement and average watch percentage. So we use region regression as prediction method and R-square as evaluation metric. We show the result of predicting relative engagement in the left plot and average watch percentage in the right plot. The letters underneath represent models with different feature sets. First, we notice we can achieve R-square up to 0.45 for relative engagement and 0.77 for average watch percentage. This suggests that average watch percentage is very predictable. Second, we notice channel-related features are the most predictive. This is consistent with previous work in predicting tweet cascade. Lastly, topic features still provide a non-negligible improvement. This is contradictory with a prior study that content topics are not important in prediction. However, we remark that they are predicting popularity, but here we are predicting engagement. This again remarks the fundamental difference between popularity and engagement. So next, we investigate which topics are more engaging. On the x-axis, we group videos by their freebase topics and plot the topic size. On the y-axis, we use conditional entropy to compute the information gain for each topic. A lower conditional entropy suggests it provides more information in predicting engagement. The color of each dot is the average relative engagement for the corresponding topic. Red is more engaging, while blue is less engaging. We find generic topics such as music and book, they are not informative. But even within small topic, baseball is not informative. On the other hand, topic of Obama and Bollywood, they give more predictive power. So to sum up this section, we propose a new metric called relative engagement, which calibrates video watch percentage against the video length. We show that relative engagement is correlated with content quality and it's stable over time. Moreover, we find engagement is predictive even before a video is uploading. So finally, I will give a brief conclusion on what I have achieved. So for all three research questions I have worked on, I list some of highlighted findings here. Generally speaking, I make contributions on understanding how social data sampling affects common measurements, how YouTube recommendation system drives user attention, and why some online content are more engaging. Altogether, methods and observation from my research can be used by content producer, hosting site, and online user to improve content production, advertising strategy, and recommendation system. So my long-term goal is to developed the principle for responsive platform by using data visualization and machine learning techniques to measure and model the collective user behavior. So here is the list of publications I have published and co-authored throughout my PhD, including 3 first authored full paper in top computational social science venue. Together with my collaborators, we have released 2 software, 2 demos, 4 datasets, and personally, I have received 2 awards. So moving forward, what will be the next topic? So I'm now working on a very interesting project that measures the political polarization on YouTube. So political polarization is a well-known phenomenon on Twitter. Here are 2 retweet networks from previous research. We can see that the partisanship is clear. Left-leaning users only tweet left-leaning users, and right-leaning users only retweet right-leaning users. They barely retweet the other party. But does this echo chamber exist on YouTube? My preliminary result suggests no. This plot is based on all comments from the last 3,000 video published by MSNBC, Associated Press, and Fox News. I observed that 42% of the users have posted comments to both left and right-leaning videos. This is larger than the number of users who only comment on one partisanship. To conduct this project, I curated a new YouTube media bias dataset. It contains nearly 1,000 YouTube channels of media outlets, over 400,000 videos they published in 2020, and millions of comments and users who comment on those videos. With this new datasets, we can answer lots of new questions, like who are the users doing cross-partisan conversation? Are cross-partisan users getting more attention measured by the votes or replies? And do cross-partisan users, they complement one party and they belittle the other? So they are all very interesting questions, and I look forward to presenting the result of this project in near future. So in the very last slides, I want to use this opportunity to thank my families who always give me their unconditional support, and my wonderful supervision panels who help me through my PhD. And also my academia siblings in the same lab, and also my lifelong friends, collaborators, and mentors. So this slide concludes my talk, and I'm happy to take questions.